Swayam Prabha. Digital India. Educated India.
Okay, good morning. Apparently I said yesterday that I'm going to talk about collisions, so that's what I'm going to do today. The plan for today is I have about 3 or 4 lectures, each of them may be 10 slides or less on collisions. And then maybe next hour onwards we will talk about very rigorous derivation of Euler-Lagrange and Euler-Euler methods. Okay, and then about those approaches, and then we will continue tomorrow with more on Euler-Lagrange and Euler-Euler. Okay, so this is sort of the last sort of theory kind of stuff. Afterwards, we are going to talk about methods. Okay. So the kind of problem that I'm thinking about is, imagine that you have a tank which is stirred. So there's turbulent flow in there, and inside, let's say there are lots of, you initially put what are called monomers, single size. Okay, and over time 2 of them collide, becomes dimer of size 2, then size 3, 4, and become larger and larger. And we want to keep track of how this collision, they have to collide and they have to coagulate. Another word for that is agglomerate. Okay. So keep this in mind that as they become bigger and bigger, you need 2 things to happen. One, 2 of them should collide, and after collision they cannot bounce back. If it bounce back, then that doesn't contribute. It contributes to collision but not to coagulation and growth. So that's something that I will talk about. So we start with monomer, and I'm going to use the notation m. M denotes the size of a particle. So this is a discrete system I'm talking about. In reality, it will be continuous. Say, for example, if you talk about rain droplet, its nucleus may be as 10 nanometers. I don't know, I'm just throwing some number. But then due to condensation it can become 10.1, 10.5, every value it can take, and when it collides, every possible size is there. But this is a much easier system that we say that we put everything at, say, 10 nanometer or 1 micron. You populate the system and let the system evolve. Okay. So m equal to 1 is the monomer. Okay, and then we are going to worry about the size of a number of them. So I'm going to put n equal to mt. So this is the number of particles or droplets or bubbles of size m at time t in the whole bucket. So right now we are not going to distinguish between this part of the bucket or the other part of the bucket. This is bucket as a whole. Okay, so we're just going to focus only on coagulation process, not the advection, how it comes from the left to the right. That's what the population balance equation did. So you remember, if you go back to the population balance equation, there was a right hand side that we said sources and sinks. Now we are focusing dead on that term, how m equal to 1 becomes m equal to 2, that is size 1 becomes size 2, and size 2 will become size 3 and 4 and 5. So that this is the source term. What could be a loss for size 1 could be a gain for size 2. Okay, and that's the kind of accounting that we are going to do. Okay, taking into account all the collisions. So monomer will, when it collides, become dimer. Dimer colliding with the monomer will become 3. Now m equal to 4 can be produced by one colliding with 3 or 2 with 2. Okay. By the way, now when you think about it, how do you create m equal to 2? By 2 ones colliding, or a 3 breaking up, or a 4 breaking up. So we are also going to take that into account. Okay. So this is no, actually not breaking up. I should be very careful here. We are not going to talk about any breakup. I take my word back. So if you look at the population of 2, new dimers get produced when monomers collide, but you also have a loss when a dimer collides with a monomer or by itself. It gets out of 2 and it becomes a 3 or a 4. Okay. So we have to take a careful look at the balance. Okay. So one example is, let us say at t equal to 0, n of 1 comma t equal to 0 is, say, a billion monomers are put in the bucket, and there is no dimer, trimer, etc. So this is our initial condition. This is a cooked up problem. I am just saying that there is a lot of monomers in there, and then I say let us wait for 15 minutes, t equal to say 10 or 15 or whatever it is. You want to know how does it look like. Now if you wait long enough, it may become like this, then more like this, etc. And how does this evolve? So in other words, this is called the number density spectrum. Initially it was a delta function at 1. There was a peak. Now slowly it shifts, it becomes broad, the height goes down, okay, the number of monomers will go down. Okay. And how does this process go? So this is, how do we describe this is the question. Now I want to think in terms of 4 terms. So we are talking about, I am going to now broaden a little bit. The number density n I showed, but I want to now talk in terms of probability. Probability, I want you to think about this. This is a probability in n with m and t as parameters. This stands for probability that there are exactly n particles of size m at time t. So in other words, we fix our m and t. So we say, okay, I am looking at monomer and I am looking at this time. Now this probability will say, is there 1 of it, 10 of it, thousands of it, millions of it. Okay. So this way we allow for the fact that at any later time this could be a stochastic process, because collision is a random process. So we are only looking at probability. Okay. So I am interested in wanting to know, I want an equation for this. I put this colon just to say, whenever you say probability, you have to say it is a probability in what? It is a probability in number. So given a fixed value of m, fixed value of time, in other words, you say monomer, dimer, trimer or particles, clusters of size 6 and so on, or 10, and you pick a time and you say how many of them are there. So this probability summed over all n must be equal to 1. So in other words, if you say m is equal to 1, you are asking how many monomers are there at time t. It has to be somewhere between 1 to whatever that number is. So this is the probability. Now we are asking at a bucket, if you knew this probability of some size particles at some time, why would it change? Why would this change? Okay. There are 4 terms here. It is going to change due to only 1 and 2 are very important, and 1 and 3 are important, and I will say more about this. So one is two smaller particles or droplets. I will call it particles, but what I am talking about is droplet. Okay. Now, I am going to also make an assumption here that everything remains sphere. So, two droplets collide, a larger droplet is also sphere. Okay. If 10 of them collide, it is just a larger sphere, just to make our analysis easy, but it does not always have to be like that, because smoke flocks and things like that I talked about, they just stick together, they do not just merge. Okay. So, there are lots of other complications, but let us make our problem simple. So, everything is spherical, only it is a larger sphere, okay, when they agglomerate. So, two smaller particles of size m prime and m double prime collide, such that m prime plus m double prime is equal to m. So, in other words, if you want m is equal to 10, you can have 1 and 9 colliding, 2 and 8 colliding, and so on, 3 and 7 colliding, etc. So, every combinations of m prime and m double prime, and of course, m prime and m double prime are smaller, because two smaller ones collide and they produce a bigger one. So, this will be a positive term. It will contribute to this probability increasing. Number 2, always I am going to, this 2 and 4 are special cases when m prime equal to m double prime equal to m by 2. So, in other words, it turns out that collisions between same size particles has to be treated slightly differently. Okay? But that is a technical detail, let us not worry about it. Later I will show 4 terms, but the point is that you, so in other words, for when m is equal to 10, 5 and 5 colliding to produce 10 is a special case, and I am putting it aside. Everybody else, I just keep it together. Now, what is 3? You can already imagine just the opposite of it, m breaking up into, I said that I am not going to study breakup problem, because that when breakup problem comes, there may be even more terms. Okay. So, we are avoiding, by the way, I want to make it clear that we are not allowing any breakup of any sort, only growth in this one. Just, and the breakup, by the way, can be treated very similar to what I am discussing, but we are not going to discuss that in the lecture to make things matters simple, because they are hard enough already. So, why would there be a loss of m is when m collides with any other particle. So, in other words, if m is 10, I already have a 10. When it collides with a 1, it is a loss for 10, because E becomes 11. When a 10 collides with a 5, loss for a 10 and a 5, and it becomes a 15. So, this one is nothing but one m size particle colliding with any other particle. Does not matter whether it is small or big, or only thing is that number 4 is an m colliding exactly with another m. Okay? Just like we did separate the 2 separately. So, here 2m collide and create a 2m particle. So, 4 is a special case of 3, 2 is a special case of 1. Okay. So, with that, I want to know this right hand side. I want to write this equation for the right hand side. So, I am going to show 4 slides where each of this term 1, term 2, term 3, term 4 are written. Okay. In fact, we are going to focus only on term 1 and 3. Just how do we take care of new guys being produced and existing ones being lost of a certain size.
Yes, as you told, in 3, one m size particle is colliding with a smaller particle. So how come the size will be m particle only? Or in 4, 2 m particles are colliding, and we are defining probability for n particles whose size are n. In term 4, when 2 particles of size m collide and coalesce, then they will form a 2m particle size.
That's right. So, when this equation for m, there will be a loss of 2 particles. Every time 2 m size collide, if there was 1000 of them, now after that collision there is only 998, because 2 of them collided and they are lost. Now, there will appear as a +1 for m is equal to 2m. The new size particle, there is a new bigger guy produced while two smaller guys disappear, and you will see it in the next slide. Okay. So, this one is the number one mechanism. How this is basically m prime plus m double prime equal to m. So, this is the right hand side first term, and I will explain what these things mean. First, we want to know how many n prime, how many particles of m prime are there, because what we are talking about an m prime colliding with m double prime. So, these two terms tell you the probability of how many of m prime and n prime are there. Let me change the color. This is the probability, this yellow term is the probability of collision between m prime and m double prime per unit volume per unit time. This C m prime m double m prime is what is the collision and coagulation kernel. Okay. I don't know what it is right now. That we are breaking the problem in stages. We are now doing accounting, and right now we are saying there is a probability at which it's going to collide, and we are going to derive an expression for the C. C is the secret of collision. Okay. Right now we are just doing bookkeeping. Okay, and we are leaving that, yeah, there is a probability at if there are 1000 m prime are there, 10,000 m double prime, this will give you what's the collision rate between those two sizes. Okay. So, this probability just tells is there a, so remember that we are saying that there are n prime of size m prime and m double prime of size m double prime are there. Now, we are doing a triple summation here because remember, if you want to produce particle of size 10, it could be 1 colliding with 9, 2 colliding with 8, 3 colliding with 7. All of them come from this summation. The first summation m prime goes from 1 to m minus 1. Okay. So, I am calculating 1 versus 9, 2 versus 8 and 9 versus 1. So, in other words, I double count, right, and that this factor half takes care of the double counting. Okay. So, in other words, 1 colliding with 9 is the same as 9 colliding with 1. So, I have double counted and I just divide by 2. Okay. And then since we are only talking about, we do not know how many m prime are there and how many m double prime are there, we say m prime's number could be anything from 1 to infinity, m double prime's number could be anywhere from 1 to infinity. Every possibility, whether there is a lot of them, small, fewer of them, everything. So, this triple summation covers every possibility of there being certain number of m prime droplets and m double prime droplets and how they collide. That whole process is in this notation. Eventually, we will get a much simpler equation, but this is the sort of the starting point. This is a very rigorous way of counting what is happening. Okay. Now, keep this in mind, what is this and what is this? What is in this yellow box is total number of collisions between n prime and m prime. This will produce one new m, right? If I were exactly n minus 1 m, I now suddenly become n m particles. If I already were in n, there is one more guy. So, because remember, we are tracking probability of exactly being n particle of size m, and if one new guy is produced, if I am already n minus 1, oh, I now suddenly become n, and therefore that comes with a positive sign. So every collision will bump the number of particles by 1, but if I am already n and I produce one more, I am going to be out. But this guy will appear as a production term for n plus 1 m particles. Okay? So this is just systematic bookkeeping. So I will explain for one of them, the rest of them I am not going to deal with it. The second thing is to take care of like particles like colliding. Okay? Let us not worry about this. Yes.
So in this, so the first summation is running from like m equal to m dash equal to 1 to m minus half.
This sum, yeah. Yeah. So how? So let us take m equal to 10. Okay, we are looking at size. Let us just give an example. Let us choose m equal to 10 and n equal to 10 to the power 4, something like this. So we are asking, we are looking at particles of size 10, and right now there is 10,000 of them. How will that probability change? That is the question. Okay. Now a new m will be produced by collision of a 1 with a 9, 2 with a 8, and a 9 with a 1. That is what is being taken care of this. Every such combination is taken care of there. But when I do this, 1 and 9 collision appears twice, therefore double counting is adjusted by this factor half. Okay. Now remember, this second summation and the third summation account for the fact that 1 and 9, the total number can be the number of particles of size 1 and size 9 can be anything. Okay, because we are talking about probability. Okay, so it could be 1. So n prime and n double prime can be random variables, and therefore every possibility is taken care of by this one. Okay, that makes sense. So this is exactly very similar in nature. This takes care of how a n particle that already is there, a particle of size m, if it collides, how will it get out? So let me not waste our time. So you start with this probability. So we started with p n of n t, and we wrote this equation, and what we are going to do is that we are going to take this, gives you number density, average number of m particle, because remember p is states whether that number being 1, 2, 3, 4, the probability associated with 1 times what is the probability of 1 being there, 2 times what the probability of the number of particles being 2, and so on and so forth. If you sum all possibilities, you get the average number, and that is the final equation you can derive. This is rigorously derived. This is what we are interested in, and this is a much more easier equation to deal with, which is saying, hey, how many particles of size, if I have on average n particles of size m, why would that number change? Whether that number will increase or decrease depends on 1, this is that mechanism 1 where 2 smaller ones colliding making into a bigger droplet, and this is a special case of 2 particles of half the size colliding and producing. So we are not going to worry about this that much. And this one is, if there was already a m particle and he collides with somebody, it is going to be a loss. Okay. So mainly these are the 2 terms that you need to worry about. So there is a source term and a sink term. Okay. And this term in a continuous version is called Smoluchowski's equation. Okay. Are you guys familiar with that? Okay. So, it basically gives you the number of any size, how does it evolve over time. Okay. So, and what matters in this one are these collision kernels are the most important ones. In other words, what is the probability? C m prime m double prime is nothing but probability of collision between a particle of size m prime and another one of size m double prime inside that bucket. And similarly, C m m prime corresponds to how the particle of size m will collide with another particle of a different size. So, much of our next lectures we are going to worry about how are we going to get those expressions. Okay. So, if you get those expressions, you can see that if you want m equal to 1, 2, let us say you want to go up to 100, you have 100 such equations tracking the number of size 1, size 2, size 3, size 4 up to 100, and you have to solve them so that you can keep track of how many numbers of monomer, dimer, trimer, size 100, etc. are there, and people have done that. Any questions on that? Yeah.
So, like we have this constant kernel, some kernel, like for aggregate. So, how we can choose between these kernels? Like which kernel is suits better to us?
We are going to talk about that. Right now, we are assuming that we know the kernel, the best kernel. Okay. If we know the kernel, how to do that? And the problem now, so that I am sort of posing that Smoluchowski's equation, it's only good if what goes in. So, garbage in, garbage out, like that, right. So, this is sort of a master plan of how to keep track of numbers. If you can put in a good kernel, your answer will be good. If you put in a bad kernel, it will get. So, we are going to discuss in the next 15 minutes how to develop kernels, okay, and what the kernel means. We are going to talk about that. Now, let me just write this thing. Imagine that you have a bucket. Just to give an example, imagine that you have a bucket and you have monomers, and every time it collides, the monomer poof disappears. It's just a magic. Okay, we play God and we say once they collide they disappear, just to see how the equation going to look like. Okay, I'm just going to. So, this equation, so there is only m equal to 1, there is no even 2, 3 anything, we are only saying one size. As soon as they collide they disappear. Okay. So, this equation will become like this. Forget the x, okay. We are not going to worry about how it varies in the bucket. We are just going to do the bucket as a whole. Okay, there are no spatial variation. So, actually, okay. So, what I am talking about, n for 1 t. This is number of monomers as a function of time. That is what this is, right. That is what the left hand side will be for m equal to 1 and x ignored. You get on the left hand side, hey, how does the number of the monomer change over time? On the right hand side, the first term is 0 because you cannot produce monomer. Okay, collisions of two small. There is only loss, so it is a minus, and number of monomer is n of 1. I missed the time there in this notation. So, this. And then you get n of 1 of t, c of 1 1. That is the equation that you get, and this is a very simple equation. What does it say is the monomers will decrease, and the rate of decrease is C11, the probability or collision, probability of collision between 1 with 1 itself, and is weighted by the number density of 1 and 1, n square is there, because the probability of how many of them are there is the number density, and since we are talking about 1 and 1 colliding, you will have n squared. So, in other words, always you have to see the number of collisions will depend on the number of the two particles that are colliding times the collision kernel. If I say 1 colliding with 2, this term will look like minus n of 1 t times n 2 t. So, in other words, number of monomers, number of dimers times probability of collision between 1 and 2. Okay. So, that is the kind of collision term, and the production terms will look similarly. So, I just this equation looks a little intimidating, but when you look at it, it's not that difficult. Okay. So, you are just keeping track of everything. Okay.
Sir,
Yeah.
What should be the left hand side of this one colliding with 2?
So let me erase some of these things and then I will rewrite it. Suppose another experiment, mental experiment that we do, where we have only monomers and dimers. There is only 1 and 2. Okay, there is only 1 and 2. So, we say that we do a system, a bucket, and we are going to consider the bucket as a whole, and monomers are there, dimers are produced. Anytime 3 gets produced, we just throw it out, 4 anything else gets thrown out. So, when you write it, number of monomers this will remain the same. Monomers have no production, they only get drained. Number of dimers what was a loss for a monomer is a gain for a dimer, but with factor half, because for every 2 guys you get only produce 1. Okay? So, that factor half comes in, plus minus every dimer will collide with itself at the probability 2 2, and this will produce 4, okay, and we just throwing it out. Okay. And you also have n of 1 t times n of 2 t C12, which is collision between a monomer and a dimer producing 3. That is a loss for 2 as well as loss. Now, actually here I should put that also here. So, there are 2 losses for 1, which is 1 colliding with itself and 1 colliding with 2, and for 2 there is a production, 1 and 1 colliding will produce 2, but 2 colliding with itself or 2 colliding with 1 will be a loss for it. It's just simple like this. Okay. So, if you want to go from 1 to 100, it is not a big deal to write. Okay. Now, the way this is written, these are ordinary differential equations. By the way, when you take courses in ordinary differential equation, this will get a matrix equation and you can solve it. Nonlinear system of ODEs. Okay. So, not difficult to solve. Okay. And people solve it and you can track. In the previous slide, I showed how the spectrum changes. Now, you can plot it, you can run this system of ODEs and you can see, you start with monomer, you see dimer producing, trimer producing it just. Now, if there is a cloud and monomers are constantly being produced, you can add another term to this right hand side here, source. If there is nucleation, if there is evaporation or other things, you could add and make it more and more complicated. Okay. But the idea is this one we keep track of a discrete system. This is a discrete system. By the way, there is an exact integral version of these equations which are continuous, which are the Smolov-Kavsky's equation. Okay. So, where there is a continuous size and how size varies, okay. There will be integrals, it is more complicated. But in all of them, we are down to finding what is C, what is the collision kernel, that is where we have come down to. Okay. Let us discuss that in the next 10-15 minutes. Any other questions? Yes.
What is the physical difference between agglomeration and coagulation?
We are going to talk about that. You are always ahead of me. So we are going to talk about that.
Two particle collision, am I right? not incorporate two particles, three more than 2m?
That probability is so low. So for that's a great question. Okay, nobody worries about 3 particle collisions. Okay, because the probability of 2 particle collision, unless very dense system, then you have to worry about granular medium kind of stuff. I am talking about rain formation. Okay, these droplets once in a while come and collide and become. So the probability of collision itself is low. That the probability of 3 guys happening is the square of that. It is negligibly small.
Will the prediction be realistic for two particle collision?
Absolutely, it is very, very good. Yeah, 3 particle collision in rain formation is not important at all. Now, on the other hand, if you have a dense granular medium where they are touching and they are always touching, it can touch with 3 or 4. So it depends on the application. I am talking about only dilute systems where chances of collisions are not negligible, but small. Yeah, yeah. So when the probability of collision is 10 to the power minus 3, not negligible, probability of 3 guys coming together is 10 to the power minus 6. It's pretty small. Okay, you can safely ignore it.
So it will be valid for a dilute gas solid system, these equations?
Well, it doesn't have to be gas solid systems. It could be sand particles, silt. This is how cohesive sediments form. Okay, clay like particles of size 1 micron clump up together and they become bigger ball of say 10, and makes a big difference on how they settle and how they transport. Or soot particles in combustion applications, they form chains. Okay, and all of them they usually collide sort of one at a time, or flocks will collide with flocks, but the collision is happening only binary. His question is, what's the chance of 3 guys simultaneously coming, and not very much. Okay. But on the other hand, if you take a packed bed of particles and you have a flow, there is enduring contact, 2 of them are touching simultaneously, so lots of complex things may happen. Okay. Okay. Now there is a lot of information. I went slower because I would rather go a little more slowly and carefully than cover a lot of material. Okay, so I will have to skip a lot of details because I don't want to get stuck in collisions alone. Okay, this is your question. Okay, so what is C? That depends on a problem. If you do a rain formation, that C accounts for the following. It accounts for a probability of 2 guys coming, hitting each other and coagulating. That C is what will be called coagulation kernel. Now typically to get there, people break it into multiple steps. Okay. The first one is called geometric collision kernel, and I will explain what it means. So you have a particle and say another particle, maybe a bigger one, coming down, and let me draw this one a little smaller. Geometric collision, in this case let us say they are all raining down. Geometric collision is if they were to follow, and if you ignore the 2 particle interaction, the fluid mechanics, okay, just by the fact that if they were to follow the streamlines without each affecting the other, what would be the chance of collision? Does that make sense? So in other words, geometric collision is only how a flow moves both the particles and what is the chance of them being brought together. But people know that when they get close together, they do not necessarily follow the background flow streamline, they can just dodge away from each other. So they say, okay, let me first, that C will be written as C geometric collision times, maybe I do not want to call it C, maybe let us call it eta collision efficiency and coagulation efficiency. This is overall. So they say, the first term says, if they were to perfectly follow the streamlines, what's the probability of collision? When you multiply by this collision efficiency is probability of collision taking local flow into account. Typically, collision efficiency, the first eta may be 70%. That means 70% of the time they don't end up colliding, even your streamline analysis says they collide, but 30% of the time they dodge. Okay. The last one is fairly easy as well to understand, not easy to model. The last eta says, well, if they collide, what's the chance that they will stick together and not bounce back? That may be another 50% or something. Okay. So in other words, we are going to try. So we wanted to model that C, which takes all of them into account, but we are going to model them in 3 pieces. We are going to say, I want to first to develop a collision, geometric collision kernel. That's somewhat easier. Then the next thing you say is that I want to understand what is the collision efficiency, and then you will model coagulation efficiency, and you multiply all of them, then you get the final coagulation kernel. Okay. I will only talk about this geometric collision kernel, because eta collision efficiency, eta coagulation efficiency are very hard. Okay. But in the literature you can find results about that. Okay. So any questions on that? So we are going to focus only on geometric collision kernel. So keep in mind that whatever we are going to, I'm going to say, you got to modify that taking into account.
Efficiencies are found only by experimental techniques. Are there any modern techniques, or empirically we can only find collision efficiency and coagulation efficiency?
Coagulation efficiency mostly empirical, because it's pretty hard. Okay. Collision efficiency, there is a lot of literature. I yesterday talked about Onishi and Jeffrey and Onishi. Their kind of analysis is used. By the way, Jeffrey and Onishi also talks about big particle and the small particle. So very close interactions you can use, and you can look into the literature. There are a few results on collision efficiency, and you can use it. But coagulation efficiency is very hard. Many times you will have to do experimentally measured. Okay. So you calculate it and then you put it in the model and you look at the experimental observation. If the actual growth is a little slower, then you say, okay, my collision kernel I'm using is not really good, so I might want to dumb it down a little bit with some coagulation efficiency. Yeah.
Sir,
Yeah.
sir, so as far as I have understood, these are all things that we have learned till now are going hand in hand with reaction engineering concepts, in which there is a collision theory for calculation of the reaction rate. So there.
What theory you said?
Sir, collision theory.
Collision theory. Yeah, kinetic theory.
Yeah, kind
Yeah, okay, this is all kinetic theory. It's just kinetic theory. Yeah, absolutely.
The Arrhenius calculation of the rate constant comes.
Yeah. Well, if you guys have already studied kinetic theory, this is big part of kinetic theory. Okay. So there are 3 ways particles are known to collide, and there are few ways. Okay, and I will tell. I have written here gravitational collision kernel, and this is basically you have a particle, bigger particle falls down faster, and smaller ones who are randomly distributed, they are falling a little slower. So this big guy, like a Pac-Man, comes and gobbles up all the guys who are on the path. and we do not have to worry in this case about the smaller guys dodging, because we are worrying about only geometric collision kernel. So, you can see that this guy sweeps out a volume. So, as he comes down, this is diameter of the ith, the big particle I, and these little guys, let me call them j. So, the big guy, you take a little bigger circle around him, because you have to take care of the diameter of the other guy, and then you draw a tube, and he is going to be sweeping and gobbling everybody in the way, right? And it depends on relative velocity. So, Cij is easy in this case, is equal to, I am not going to derive it, it is in the book, you can rigorously derive, is to be 4 by 3 pi density ratio minus 1 72 viscosity of the fluid times g. Instead of diameter, let me write it in terms of volume, volume of the ith particle to the power 2/3 minus volume of the jth particle to the power 2/3, their difference absolute value. Volume of the ith particle to the power 1/3, jth particle to the power 1/3 to the power 2 plus. So, you can see this is the tube's diameter. This takes care of the relative velocity. If both of them are falling at the same speed, then there is nothing to be swept. So, the rest is little detail. So, now it is a rigorous expression, and this is only for gravitational mechanism. So, if particle in cloud physics, this is one of the most important one other than turbulence. Okay. So, in other words, if collision happens mainly because of falling, this would be a very good one, but then you have to multiply by collision efficiency and you have to multiply by coagulation efficiency. This is only geometric. So, let me just tell you, there are few other mechanisms by which collisions can happen. One is Brownian motion. Even if there is no flow and you put particles in there, they are randomly jiggling, and this works only for submicron particles, because they so in other words, for soot particles it is really important. Okay, they randomly move, Brownian motion, and they coagulate. Gravity we already talked about. 3 is shear. Okay. Shear is nothing but, let us say you have a shear flow. Now, for gravity you must have different size particles. You can never, two particles may not collide by themselves. Okay. But that is not entirely true if we take collision efficiency. Their collision efficiency can work the other way. Imagine two particles. A geometric collision will say, yeah, both of them falling down. But yesterday we saw that the guy who is in the behind has a lower drag, therefore he is going to come faster and he is going to collide. So, two particle interaction can not only make the particle dodge, but he can also make particles collide which otherwise would not have collided. Okay. So, collision efficiency can be greater than 1. Okay. Take that into keep that in mind. The shear mechanism can happen with even like particles. The one who is above or slightly above is going faster than the one who is, so is going to come and collide, and a little bookkeeping calculation you can find. So, you want to know how this collision kernel happens. So, you put a sphere of diameter di plus dj. Okay. So, in other words, you take around one particle and you put a halo around it, and you want to know what is the probability of the second guy entering that cage, and that will give you the collision. Okay. So, you can calculate that. Now, a special form of shear is turbulence. Turbulence is basically also shear. There are a lot of eddies going around, so particle may come and turbulence will make another droplet, one droplet collide with another droplet, and this is a very important mechanism in say rain formation. Okay. And the last one I want you to think about is inertia, and the inertia also will work only for unlike particles. Like particles won't work. Let us say your fluid streamlines are going in circles, and let us say you have now lots of small particles there. They are being spun around, they are pretty much going with the flow, and maybe a little bigger particle whose trajectory is like this, he is spinning out. It is just like gravity, the same as gravity. Because of inertia, this bigger particle is not following the streamlines nearly as well as the guys smaller ones, and that creates a relative velocity. The key is any time you have some sort of relative velocity, either by gravity, either by inertia, or by turbulence, or by shear, you have collision. So, for each of them there is Cij. For shear it will depend on shear, for inertia it will depend on the Stokes number of the particles, for turbulence it will depend on local turbulent velocity fluctuations. So, there are exact models written for them. The real challenge is when many of them act together, how do you combine them, and people have come up with some empirical formulas. Okay. So, I will not give those formulas because they are going to look like this, longish. If you have multiple mechanisms, it gets even longer, but you have Cij, which is only geometric collision. Okay. Now, there is some effort on collision efficiency and much less on coagulation efficiency, and you put them together and you put it in the equation that I showed, and the continuous version will be Smoluchowski's integrals, and you now describe collisions. Okay. Any questions on that? We will take a break now.